At constant temperature and pressure, if delta G of the system is negative, the reaction is spontaneous. If it's positive, the reaction is not spontaneous. And if delta G absolute is 0, the system is at equilibrium. So later on, we're going to make a distinction between delta G of the system absolute, like we see here, and delta G of the system at standard conditions. They're related. So standard conditions is the free energy change that accompanies 1 mole of a compound from its elements at standard conditions. So just like delta H, delta G of formation for elements is considered 0. Unlike S, where we can get a absolute value for how disordered something is. We can't do that for delta G because it's got a delta H component. So elements are considered 0, and we put them together to make some compound. We see what the free energy change is in terms of kilojoules per mole. So again, those are delta G naughts of formation. Elements at standard state being put together to form compounds. Any other delta G naught change is considered a delta G naught of reaction, measured in kilojoules. So sum of the delta G of the products minus the sum of the delta G of the reactants gives me the change in the delta G of reaction at standard conditions. Oh, just wanted to quick point that out, right? Right. So like I said, standard free energies of formation for any element in its stable form is 0. So just like delta H. All right, so calculate the standard free entropy change for the following reactions at 25 degrees Celsius. So just like with delta H, you're going to have thermodynamic data. You'll have a delta H column, an S column, and a delta G column. So you can look up the free energies of formations of the reactants. You can look up the free energies of formation for the products and subtract the reactants from the products to figure out what the change is. So get a negative sign on delta G naught, right? And this tells you that it's a spontaneous reaction. A very spontaneous reaction, right? I mean, we burn ethene, it's to completion, right? It's gone. Any combustion reaction, you're going completely forward, right? So we expect a big release of free energy. All right, delta G naught is equal to delta H minus T delta S. So how do we apply this? All right, so there are going to be situations that are going to be exothermic, where you begin becoming more disordered. That means it doesn't matter what you do that temperature, right? It's always going to be spontaneous. You've got both things working for you towards trying to make delta G naught negative. If you have an endothermic reaction where you're becoming where you're losing disorder, well, this tells you you're never going to be spontaneous. No matter what you do to the temperature, you're always going to have a positive value for delta G naught. All right, you're always going to have to put free energy in. So again, if you look at delta H at the top and the relationship to delta S at the top, when one term dominates, right, like for example in the next one, you have an endothermic reaction, right? The positive delta H is making delta G positive. But a positive delta S, right, a negative delta T times a positive delta S is a negative term, and that makes delta G negative. So at high temperatures, the delta S term is going to dominate over the delta H term. When you have an exothermic reaction and delta S is negative, all right, so delta S being negative is going to, negative times a negative makes it positive. So at high temperatures, that term will dominate over the fact that it's exothermic and make it non-spontaneous. So these buttons are clickable to see examples, right? So looking at the first example, right, exothermic reaction that's becoming more disordered. For example, the decomposition of hydrogen peroxide, which, as we showed in class, is a very slow reaction, but very spontaneous and spontaneous at all temperatures. So you've got both terms, right? The delta H, the negative delta H making delta G negative, and the positive delta S, right? Negative times a positive is a negative. So both terms are making delta G not negative. If delta H is positive and delta S is negative, then it can never be spontaneous. So, for example, oxygen turning into ozone is never spontaneous. This is why it doesn't need any help. Ozone doesn't need any help being destroyed by chlorine radicals, right, from CFCs. So anyway, back to our thermodynamics, right? Both terms are making delta G positive. Positive delta H makes delta G positive, and a negative times a negative makes the delta S term will make delta G not positive. So both terms are going against spontaneity. Positive, an endothermic reaction that's becoming more disordered, right? So at high temperatures, right, the fact that you're becoming more disordered will dominate over the fact that it's endothermic, right, and make it spontaneous. So like way back when we started this conversation, this is the reason why some endothermic reactions are spontaneous. It's because they're becoming more disordered, and at high temperatures, that term will dominate over the fact that it's endothermic. Exothermic reactions, where the delta S value is negative, you're losing entropy. So a negative times a negative makes it positive. So again, at high temperatures, ammonia reacting with hydrogen chloride, right, we're turning into a solid, right, we're definitely losing gas here. So the delta S term is going to be negative. At high temperatures, this is going to make this reaction non-spontaneous, even though it's exothermic. All right, so we're sticking with this one, right? Ammonium chloride solid turning into, I'm sorry, different one. Solubility of ammonium chloride, right? Ammonium chloride solid going into solution. So I can look up the delta H formations for the products and reactants. I can look up the S values for the products and reactants. We're at 25 degrees Celsius, so I know my temperature, so I can plug in. First get the delta H and the S value. Now notice these units are different. This is the important point, right? Delta H is in kilojoules, right? So heat changes always have a greater magnitude than entropy changes, which are in joules. So they have to be in the same unit if you're going to plug into delta G is equal to delta H minus T delta S. They both have to be in the same unit. So we convert delta S into kilojoules, right, by dividing by 1,000. So convert joules into kilojoules, and then we can plug into the equation. Temperature is 25 degrees Celsius, 298 Kelvin. So I can plug those numbers into the expression for delta G and solve for the magnitude of delta G. So this is a spontaneous reaction at 25 degrees Celsius. Let's see, what do we have? We had a endothermic reaction that was becoming more disordered. All right, so at 25 degrees Celsius, there's enough disorder there to make this spontaneous. Which, hey, we already know, right? At 25 degrees Celsius, ammonium chloride solid is soluble. High temperature, no, I guess at low temperatures, though, it would be non-spontaneous. This would be something less spontaneous at low temperatures, right? Right. No, high temperatures. At high temperatures, this will be more soluble, right? So you'll be dominating over the fact that it's endothermic. That's what we want to get there. Of course, if we had the data, we could just look up the delta G's of formation for the products and reactants and plug into products minus reactants. So there are values for ammonium chloride solid at 25 degrees Celsius, ammonium ion aqueous, and chloride ion aqueous. So we plug them into products minus reactants, and we get the same answer. So you got to be able to do both. Use products minus reactants to figure out delta G, and plug into the equation to figure out delta G.